not with volume, sorry, with radius bigger, then we can think of these, we can model the sphere as an infinite sum of cylinders of infinitesimal height, or we could call them those disks because it's less of a mouthful. So, what does it look like? So that looks like, obviously, this, that. And then I've slightly better drawing here, and we've got and then an equation form that's in, if we're thinking about the surface area and volume, we can just do we can just do the sum of the surface area and volume of every single cylinder. So that's what's represented here. We've got the two there because because if we only do 0 to r, it's that. But then but then we need to get the sum. We need all of that more. So that's why we have the two there. Now, for actually deriving the formulas, what we use is we do here is we define, obviously, as you can see, the radius of the sphere is bigger, the radius of the cylinder's circle, or the radius of the disk, I guess, as would probably be more accurate, as r, um, which means that we have, then obviously because it's the same axis, obviously we've got y here, we can define y as h, which then Pythagorean identity, same thing for z and r. And then if we differentiate both sides, we can get this. And that will allow us to change coordinates for the volume. And then for the surface area, for the height, we'll be using the arc length here. And the formula for arc length is r theta. And then we use the values from our sphere. And we differentiate both sides, obviously, so that we can actually so that we can, again, create a change of coordinate systems, not coordinate systems, change of coordinates. So we've got that, and then we have the infinitesimal change in height, infinitesimal change in height for the surface area, which is the infinitesimal change in the arc length. Same thing for volume for delta H, and then the tiny changes in uh, theta, obviously, which is what our functions are going to be in terms of, which is what we use to which is the reason we bring everything in terms of theta. So, because then if we're integrating with respect to theta, then we can do 0 to pi, because that will be the entire surface area of here, of here, of here, of here. We can represent the area function obviously as this, and then sub in the coordinates, change of coordinates, and then evaluate.
Well,
So,
can I just
and
say
then
thanks,
that
guys?
will
Well
give us
done. That was great. I've programmed for 30 years,
our
and
formula of
one of the
4
things I
pi r
lament
squared,
is
and then
not
a
being
very
able
similar
to
thing for volume,
load up programming in the subject. But
just
I have to be very disciplined and not
pi
do
to
it
2
because
pi, which is just
of the 300 odd
that,
students,
which will give us,
there's only about half who
again,
can code.
I should,
So
will give us,
it really means a different
again, the
project, and
entire
I'm
volume,
thinking about that and talking about that with the powers, about having
because this would
targeted computer science
more
projects
accurately look
versus
like
other projects.
this.
But that all needs to be fleshed out because we don't want to present as if there's
So,
some kind of advantage
we
or
use
disadvantage depending on which type
substitution,
of
and then
project
it's
you do.
just
But that may or
pretty
may not happen in the future,
straightforward.
and
We
it's
get 4 pi
yeah.
r squared.
But I
So,
enjoyed it. Thank you.
it's pretty obvious then that the derivative of the volume is equal to the surface area. Now, why is that? I think the easier way to look at this first is using 2D. So, if we think of the area of a circle, we can think of it as not just like the infinite sum of all the lines from here to here, like within this, but instead the circumference of all the circles between radius 0 to r. and then we can do and then obviously that in terms of in terms of an equation we can show that here. So let me just change it to there. So we can show that there, and then in 3D we can think of it as like this. Obviously, there's like infinitely many in here, but it's that sort of idea. It's all of these. So then again, using the sum function, and then as we did as we did for the derivation, change the idea, like convert it to integral form. We can derive the in we can derive the the volume of the surface area using this idea. So that's I guess that's our reason for it. Um, yeah, thanks for watching.